Describe how a balloon rocket works and how conservation of momentum explains rocket motion. The materials needed: balloon, long shape, tape, string, nylon if available, paper clip, and stroke pinch of starch. Procedure: first, insert the string into the stroke before stretching it over two posts. You can use chairs or iron stands as posts. Make sure that the string is taut. Second, put a pinch of starch inside the balloon before inflating it. Twist the open end and temporarily secure it with a paper clip. Third procedure, tape the straw to the balloon such that it is aligned with the balloon's opening. Fourth, position the balloon at the middle of the string. Fifth, release the air from the balloon by removing the paper clip and observe carefully. And lastly, draw a diagram showing the momentum vectors of your balloon rocket and the air. Answer the following question. For the first question, what can you say about the initial momentum of the system before releasing the air from the balloon? Second, what did you observe after releasing the air from the balloon? Third, what is the direction of the balloon compared to the direction of air coming out from the balloon? Fourth question, how do their momenta compare after releasing the air? Fifth, from your answer in question 4, how does the velocity of the air that is pushed off the rocket compare to the velocity of the balloon rocket?
Second activity, conservation of mass.
Solve the following problem. For the first problem, when these two freight cars of different mass collide and couple, what will be their resultant vector? A large locomotive with a mass of 4 kg collides into a 1 kg motionless railroad car collides and couples together. What is their combined speed after the collision?
To deepen your understanding on this topic, let's have this activity.
Deepen. Number 1. Make two event chains showing what happens when a rolling ball, the ball 1, hits a resting ball, which is the ball 2. For number 2, use the phrases gains momentum, hits ball 2, is hit by ball 1, loses momentum, rest, rolls, slow down, starts rolling, ball 1, ball 2.
Before we start our next lesson, let's have an activity. All the pictures are the different types of collision. Identify the different types of collision that illustrated by the picture. Choose your answer in the box. Number 1. Correct. Number 2. Correct. Number 3. Correct. Number 4. Correct.
As you go about your day-to-day activities, you probably witness many collisions without really thinking about them. In some collisions, two objects collide and stick together so that they travel together after the impact. An example of this action is a collision between football players during a tackle. In an isolated system, the two football players could both move together after the collision with a momentum equal to the sum of their momenta or the plural of momentum before the collision. In other collisions, such as collision between a tennis racket and a tennis ball, two objects collide and bounce so that they move away with two different velocities. The total momentum remains constant in any type of collision. However, the total kinetic energy is generally not conserved in a collision because some kinetic energy is converted to internal energy when the objects deform. Since we already identified what collision is, let's proceed to the different types of collision. Perfectly inelastic collisions. Perfectly inelastic collisions can be analyzed in terms of momentum. When two objects, such as the two football players, collide and move together as one mass, the collision is called a perfectly inelastic collision.
Likewise, if a meteorite collides head-on with Earth, it becomes buried in Earth and the collision is perfectly inelastic. Perfectly inelastic collisions are easy to analyze in terms of momentum because the objects become essentially one object after the collision. The final mass is equal to the combined masses of the colliding objects. The combination moves with predictable velocity after the collision. Consider two cars of masses m1 and m2 moving with initial velocity of v1 and initial velocity or the v2 along a straight line, as shown in the figure 3.2. The two cars stick together and move with the same common velocity or the final velocity along the same line of the motion after the collision. The total momentum of the two cars before the collision is equal to the total momentum of the two cars after the collision. Perfectly inelastic collision, take note that the momentum is mass times velocity. Therefore, the law of conservation of momentum in perfectly inelastic collision is mass of the first object or m1 times the initial velocity of the first object or v1i plus the mass of the second object or m2 times the initial velocity of the second object or the v2i is equal to the combined mass of the object m1 plus m2 times the final velocity. This simplified version of the equation for conversion of momentum is useful in analyzing perfectly inelastic collisions. When using this equation, it is important to pay attention to signs that indicate direction. In figure 3.2, v1i has a positive value, m1 moving to the right, while v2i has a negative value, m2 moving to the left.
For example, a 1,850 kg luxury sedan stopped at a traffic light is struck from the rear by a compact car with a mass of 975 kg. The two cars become entangled as a result of the collision. If the compact car was moving at the velocity of 22.0 meter per second to the north before the collision, what is the velocity of the entangled mass after the collision?
We analyze the problem given the following quantities. Mass of the first object is equal to 1,850 kg. Mass of the second object is equal to 975 kg. Initial velocity or the v1i is equal to 0 meter per second. Initial velocity or the v2i is equal to 22 meter per second to the north. Find the final velocity. Let's solve the problem using the equation for perfectly inelastic collision. Mass of the first object m1 times the initial velocity of the first object v1i plus the mass of the second object m2 times the initial velocity of the second object v2i is equal to the combined mass of the two objects m1 plus m2 times the final velocity. The formula for finding the final velocity is final velocity or VF is equal to the mass of the first object m1 times the initial velocity of the first object v1I plus the mass of the second object m2 times the initial velocity of the second object v2I all over the combination of the mass of the first object and the second object. Substituting the given values to the equations, final velocity is equal to 1,850 kg times 0 meter per second plus 975 kg times 22 meter per second north divided by 1,850 kg plus 975 kg. So the final velocity is equal to 7.59 meter per second to the north.
Another type of collision is elastic collision. In an elastic collision, two objects collide and return to their original shapes with no loss of total kinetic energy. After the collision, the two objects move separately. In an elastic collision, both the total momentum and the total kinetic energy are conserved.
Momentum and kinetic energy are conserved in an elastic collision. Mass of the first object m1 times the initial velocity of the first object v1I plus the mass of the second object m2 times the initial velocity of the second object or v2I is equal to the mass of the first object times the final velocity of the first object plus the mass of the second object times the velocity of the second object. Remember that V is positive if an object moves to the right and negative if it moves to the left.
For example, a 0.015 kg marble moving to the right at 0.225 meter per second makes an elastic head-on collision with a 0.030 kg shooter marble moving to the left at 0.180 meter per second. After the collision, the smaller marble moves to the left at 0.315 meter per second. Assume that neither marble rotates before or after the collision and that both marbles are moving on a frictionless surface. What is the velocity of the 0.030 kg marble after the collision?
Analyzing the problem, here are the given quantities. Mass of the first object is equal to 0.015 kg. Mass of the second object is equal to 0.030 kg. Initial velocity of the first object is equal to 0.225 meter per second to the right or 0.225 meter per second. Initial velocity of the second object is equal to 0.180 meter per second to the left or negative 0.180 meter per second. Final velocity of the first object is equal to 0.315 meter per second to the left or negative 0.315 meter per second. Let's find for the final velocity of the second object.